bound and lower bound. Okay, it's an upper bound versus lower bound. We consider that A be a subset of R such that A is non-empty, right? So I'm considering a non-empty subset of R. Number alpha in R is said to be an upper bound of A if alpha is bigger than X, right? For every X. That is, alpha is an upper bound. Alpha is an upper bound. An upper bound of A if for every X in A, X is less than or equal to alpha. Right? That means if I look at my set, say suppose on a real line, I look at on a real line. If I look at the real line, okay, and if I look at the if I look at this, right? Say this is my set A here. Pen to kind of rotate this. So if this is A, right, all elements of A are on the real line. Okay. Then any number, say alpha, which satisfies this, that means all the numbers here must be less than alpha. Right? Would be called as a bound of the set. Means you must have a real number such that all these numbers are less than alpha. Now remember one thing: if alpha is a lower bound, anything bigger than alpha also serves as lower bound. Right? So idea of mark here, if alpha is an upper bound, then alpha plus epsilon, where epsilon is positive, is also an upper bound. This is fine. So if alpha is a lower bound, upper bound, anything bigger than alpha will also serve as a. Let's look at the definition of. Let V be a non-empty subset of R. Okay. A real number beta in R is said to be an, or A rather, a lower bound of B if what happens is beta is bigger than, sorry, if beta is less than or equal to X for every X in, that means beta must be less than every element of the set. Right? So the line which is just drawn, I can take another line that matters. So if I look at the same picture what we have drawn, if I look at this as this was my corresponding set, right? So this is my B, then any number here which is bigger than all this, right? We have taken beta for that matter. Uh, so that's the idea. Let's write a remark again here. If beta is a lower bound, then beta minus epsilon, or all epsilon greater than 0, is also a lower bound of b. Then you just take any number smaller than we note that um, um, that alpha is not an upper bound of a set A if there exists x in A such that x is bigger than alpha. Similarly, beta, alpha in R, of course, beta in R is not a lower bound of a set B if there exists x in A, x in B rather, right, such that um, x is less than beta. You cannot have something any lesser. I mean, you cannot have a element less than the lower bound in the set. Similarly, you cannot have a element bigger than upper bound. That's kind of idea we have for upper bound and lower bound, and then we have seen certain examples of lower bound and upper bound. So, right, let's look at more definitions. Definition one: a non-empty subset of R is said to be bounded about if there exists alpha in R such that alpha is an upper bound. Similarly, a non-empty subset B of R is said to be bounded below if there exists beta in R such that beta is a beta is a lower bound of, maximum. So look at that next idea. Um, so call supremum as least upper bound. Supremum. So let A subset of R be a non-empty subset of R, okay, such that A is bounded above. It means there exists at least one upper bound. An element M in R is said to be the least upper bound of A if 1 M is an upper bound of A. Second, if N is any other upper bound of A, then M must be less than or equal to A. Right? Any other upper bound must be bigger than or equal to the least upper bound. Right? Example, look at the example here. Draw a real line. If I consider the interval 0, 1, what happens is 0 is any other upper bound would be here, right? Like minus, sorry, any other lower bound would be to the left of 0, like minus 1, all are the lower bound. Least of them is 0, so 0 for this side is, sorry, 1 first of all is the supremum, right? Not define what is the lower bound or least, greatest lower bound. First of all, let us do that before I come back to this. Better I will define that. So what we have is define something called lower bound. Call this as infimum. Okay, right. Let's define that. Let A be a subset of R. Use that. Let A be such that A is non-empty. Okay. Let me put it in a proper way. Let me put this in a different way. Let A be a non-empty, a non-empty subset of R such that A is bounded below. Right? So I'm taking a subset of R which is bounded below. An element M in R is said to be the least, sorry, said to be the greatest lower bound, said to be greatest lower bound, to be the greatest lower bound, greatest lower bound if 1 M is a lower bound of A, and second would be if K is any other lower bound of A, then K must be less than or equal to, because it's a greatest lower bound, right? Note one thing, that least upper bound and greatest lower bound are, so least upper bound and greatest lower bound are unique. So let's see this in following examples. Okay. So Examples. One. Okay. So let's look at the first example. Let me take a set A to be set of all 1 plus 1 by n and belongs to Z. Okay. I'll give you examples. I'll do some and rest you can try. B, let me take 1 by n, such that n belongs to n. Then 3, C, I'll take n here. N in n. Okay. Set of all minus 1 raised to n, n in n. Then fourth one, P, I take set of all x in R such that x square minus x minus 6 is less than 0. Fifth one is set of all 1 by n minus 1 where n is natural number. And sixth one I can take f to be set of all x cos x that 0 is less than or equal to x less than or equal to pi by. These are my examples. All right. So marker. Okay. So if I look at the first set, if I'll write this explicitly, then what I would have is I would start with 2, right? Then 1 plus half, that is 3 by 2. Then 1 plus 1 plus 3, that would be 4 by 3, right? And then it would be 5 by 4, and it would be then 6 by 5, and it would be so on, right? So if I kind of draw this, our intuition would help us to tell us what exactly would it go. So what I'm trying to do is I want to find whether or not I would have a, yeah. So if I kind of draw a line, uh, kind of draw a line for that matter, okay. Then let's start with 2. Start with start with 2 here. And then what happens is I go exactly the midpoint of 2 and 1. The midpoint of this, that is 3 by 2. And then I start getting closer and closer and closer and closer and closer and closer to 1. Right? Each time this all numbers are bigger than 1, right? So what happens is as I go on, look, the number the top half, like the numerator otherwise, is always bigger than the denominator. As you go along, what will happen is you'll get 100 by 99, then 101 by 100 and so on. So what happens is these numbers, whatever we get, is always bigger than 1. Therefore, what we have is this lower least upper bound, right, of this set would be first of all these numbers are bigger than 2. So sorry, all these numbers are less than or equal to 2. So the least upper bound, first of all, would be be 2, and greatest lower bound would be, that's the observation. We still have not proved exactly whether this is the case, but this is just the observation we have made here. So for the time being, let's just understand what exactly the lower bound and upper bound is. And as the time progresses, we would just look at how actually we prove, okay, prove the corresponding things. All right. Okay. If I look at the similarly, I mean, if I look at the second example in the same line, okay, so what happens is the same set, it's one half and goes on, right? One third and so on. So what happens is this all numbers are less than or equal to one almost. Okay. So you can make out that this greatest lower bound of this set, and all these numbers are bigger than zero. So greatest lower bound would be zero, least upper bound would be. And in a similar fashion, one can check what would be the upper bounds and lower bounds for the subsequent examples which we have already taken. So I would want uh, you all to go through and just check what exactly is the case with the other things. Okay. Well, cos is a nice way. I would just look at the sixth one. That's f. This, by the way, is b, I suppose. It's set of all cos of x, right? Where x is between 0 and pi by 2. So if I look at the graph of cos, right, between 0 and pi by 2, then what happens is cos of 0 is 1, right? And what happens to pi by 2, it comes out to be 0. So what happens here is the biggest number cos the value cos can take is, right, would be at cos of 0, right? That would be 1. And the least value cos can take in this particular interval is at pi by 2. So cos of pi by 2 would be 0. Therefore, what happens is least upper bound of this set would be 1 and greatest lower bound would be, right? Similarly, one can check other examples and check out that whether it is a suprema, whether they are bounded and they are not bounded, and so on. So bounded above and bounded below. So this all sets are bounded above as well as bounded below. One can, immediately check that, right? All right. Let's look at the following here. What we have is write down explicitly. Uh, so let be an empty subset of R, subset of R, such that that A is bounded about R if alpha comma beta in R are least upper bound of A, then alpha must be equal to beta. That means if you have supremums, right, then they must be equal, right? So supremum of a set is unique is the proof. So let's look at this one. So let me name this as uniqueness of supremum. All right. Since alpha and beta are supremum m's of A. This implies, first of all, that alpha and beta are upper bounds, right? It cannot be supremum without being an upper bound, right? So are upper bound of, so therefore, since alpha is an upper bound, so alpha is a least upper bound. Let us use that idea. Alpha is a least upper bound. I'm using both the ideas, supremum or least upper bound, whatever it is, of A. Both are same. This implies that alpha is less than every other upper bound, right? Every other upper bound. Therefore, in particular, alpha must be less than or equal to beta, because beta is also a upper bound, right? So since alpha is the least of them, alpha must be less than or equal to beta. Let me name this as 1. The same process, similarly, since beta is a least upper bound of A, least upper bound of A, this implies beta is less than every other upper bound of A. This would imply that beta is less than or equal to 1. This is 2. In particular, this is 2. Right? So from 1 and 2, what do you get? Therefore, from 1 and 2, alpha becomes equal to, right? So that's the proof of the theorem. Similarly, one can show that, that is left as an exercise. Show that infimum of a set, of a subset rather, infimum of a subset of R, if exist, is unique. Proof left. The similar lines you can prove that you take two terms and show that they are both equal. Let's look at next result. Call this as generally order completeness of real numbers. Okay. Special name is order completeness of real numbers. Let's kind of put the thing in a bracket. Okay, it's called as order completeness of real numbers. Let's look at both the ideas. Okay. The first one is actually there. So every it doesn't look weird. It's so natural, you know. Every non-empty bounded subset, bounded above, bounded above subset R has a least above, right? Similarly, every bounded below non-empty subset of R as a greatest lower bound. Let's prove this. Okay, so if whatever you see, let's highlight that. Whatever you see in the bracket is the property which we are dealing with. It's called as the autocompleteness of R. It's called as the least upper bound property, of R. Okay. Uh, okay. So what we would do is, to prove this, we'll assume this. Okay, and then we would do vice versa when we are actually proving the above, the below. This is what we call as LUB property of R. So how to prove this? Okay, so let's consider, let S be a non-empty bounded above subset of R, right? Let S be a non-empty bounded subset of R. What I want to show is, I want to show that S attains um, supremum, right? All right. So since it's bounded, I will have an upper bound, and I can always talk about all the upper bounds of the set. So let A be the set of all upper bounds of, that is, A be set of all alphas, or set of all p's rather, whatever you want to call it. Already used alpha. Let A be set of all let, let, let A be set of all p's, right? Such that P is an upper bound, right? So since S is bounded about, I can have one upper bound, right? Bounded about. This would imply that A is, because since it's bounded about, you can have a lower bound. Okay, right. So let's proceed. So that's what let I take an element x and y. Note that note that x is less than or equal to y, right? For every x in. Okay, so let's look at this one. Just take an element of. Okay, let's look at this. So let me take two elements, one from S and one from Y. So what is the relation between X and Y? Since first of all, X is an element of S and Y is set of all, A is set of all upper bounds of S. This would imply that X is always less than or equal to Y. Right? That makes sense, right? The reason here being, as Y's are upper bounds, upper bounds of of S, right? They are upper bound of S. Right? Also, what would happen is X would be less than or equal to Y, right? So this would be true. Therefore, if I take any X, this would be true. So what happens is X would be less than or equal to Y for every X in S, right? Also, since Y are the upper bounds, right? This means you take any y, it would be bigger than given x, right? So this would be true for all y in A, right? Since the property of the upper bounds is true, okay, right? Therefore, what happens is, therefore, every element of S, right, is a lower bound, right, of A, right? This implies that A is bounded below, right? If I sketch the figure for you to understand this line so that I can draw it proper, okay? Uh, so what happens is my A is here. Okay, let me draw my A here. So this is my A, right? And my upper bounds are starting from here. I'm collecting all upper bounds, right? So this is my, sorry, I made a mistake. This should be my S, right? And this should be my, right? So what happens is every element here is less than this because these are all upper bounds. And you take any upper bound, this would be less, or this would be greater than every element here. So if I collect this set over here, right? If I collect this set, right, entire set, every element of S becomes a lower bound for A, right? And every element of A becomes an upper bound of S, right? So what happens is this S serves as set of all lower bounds of A, right? And therefore, what happens is A is bounded below, right? So if A is bounded below, then by the property which we said is true, let's go to that, right? I said that I'm gonna assume this. I'm gonna assume this property, right, to prove this, right? So it says that every bounded below non-empty subset of R has a greatest lower bound. So this means what? This means that therefore by let me proceed by 2, we get we have we conclude that A admits in infimum in, right? Let me call that alpha. Say therefore therefore what happens to alpha is nothing but infimum of A, right? Fine, right? So therefore, since alpha is the infimum of A, therefore alpha would be less than or equal to every y, right? For every y in, since it's an infimum of A, therefore every y, right, would be bigger than infimum, because infimum is the um, first of all, it's the greatest lower bound. It's a lower bound. That means every element of the set must be bigger than or equal to alpha. So now let x be any other lower bound, okay, right? If I start with any other lower bound of A, then what's the relation between x and if I look at lower bound of A, what would be the relation between that? Okay, is what I want to say. Right? And here that happens is, then since x is any other lower bound and is the alpha is the greatest lower bound, therefore x would be less than or equal to alpha, right, for every first of all, as I said, uh, if I go back, all these are lower bounds, right? All these guys here are lower bound for A. So if I take any other lower bound element of S, then uh, alpha becomes the since alpha is the greatest lower bound, it must be less greater than or equal to every other um, lower bound, right? Because it's the greatest lower bound. So this is true for every x in. Right? So let me name this as 2, and let me name my first equation where I said that um, where I said that yeah, I said that where let's just go ahead. Yes, this one. This is true. Right? For every y in A, this is what we have. Yeah, where I said where we said m is the alpha. Yeah, here it is. So from here, what happens is first of all, alpha is less than from here. So therefore, one implies that alpha is the uh, well, first of all, uh, yeah, alpha is the element, right? So it's a least of all the upper bounds of A. So um, yeah, so let me write that. So from 1, what we get is this tells me that every element. So from here, note that 1 tells us that, or let me take 2. 2 tells that alpha is the lower bound. Oh, make some blunders today. Okay. First of all, this tells me that alpha is the upper bound. 2 tells me that alpha is upper bound of S. Okay. And what does 1 tells me that alpha is the least of all the right, right. Alpha is 1 tells me that alpha is the least of all the upper bounds, and 2 tells me that it's first of all a lower bound. Okay, alpha, whatever we have taken alpha as. Right? Therefore, uh, we have the theorem. Hence the proof. Right? Similarly, one can try for the second part just by taking. So that also we can try and finish off. Um, so second part is assuming the order completeness. So let me take some different notation. Let M be set of all. Okay, I've already taken S. R. What I can take. Let M. Let me take M for that matter. Let M be the non-empty subset of R. Non-empty subset of R. That is bounded below. Right. Uh, let B be set of all P such that P is a. So if it's bounded, I can have all the lower bounds, right? P be all the lower bounds, right? Of B of B. Note that as M is bounded below, M is right. So the same argument. Let X belongs to M, Y belongs to B. Therefore, X is less than or equal to Y, right? As y is, oh, made a mistake. The other way, it should be other way now. Uh, dear, dear. It should be other way now because I'm looking for yes, right. So I'm taking an element. Okay, so let's draw that and understand. Drawing would help us to understand the what is happening with this today. Okay, so let's understand by drawing a figure. Boy, oh boy. Let us draw a line, right? And so what I have is my set is here. The other part, my A is or what I have said, M rather is here, and my B, that is the set of lower bounds, are here. This is my B. So my X is here and my Y is here, right? So what happens is in this case Y becomes less than or equal to X, right? And both are arbitrary elements all since B is a set of all lower bounds. This implies that first of all Y is less than or equal to X for every X in M, right? Also, also you take any y from this, it would be always less than every element here, right? So also what happens is y is less than or equal to x for every y in B. Therefore B is bounded above, right? And a set of all the elements of the set M, right? Therefore, by order completeness of R. Therefore, by order completeness of R, what happens is B admits is least upper bound. Let me say that to beta. Therefore, beta is LUB of B. Therefore, what happens is since is the least upper bound of P, therefore, what happens is least upper bound of P. So what happens is with any element of B, therefore Y must be less than or equal to beta for every Y in one thing, right? Name this as one. Let X be any other upper bound of P, right? If I take any other upper bound of beta is the least of n. Therefore, what happens is beta would be less than or equal to. And what are the upper bounds? Upper bounds are all. What are the upper bounds of the set? These are all in B, right? So this will be true for every x in for every x in B, right? So this is true. Therefore, from 1 and 2, the same idea, right? What this tells us that B is bounded below, right? And then this tells us that beta is the greatest lower bound of B, right? So, therefore, what does this tell us? Therefore, beta is minimum. From here, what happens is every element of B is bigger than beta, that means beta is an upper bound, and beta is the greatest of all the